Tumbler Snapper, a double objective operation conducted by the Atomic Energy Commission at the Nevada Proving Ground during April, May, and June of 1952. The Tumbler phase, designed primarily to obtain experimental data on blast pressures from nuclear explosions for preparation of height of burst curves. The Snapper phase, primarily designed to give information on development of new weapons. Additional benefits of the tests included troop indoctrination and participation, and some additional weapons effects information. The Tumbler operation was set up to get experimental data on blast pressures obtained from nuclear explosions at different heights above the ground. At Operation Buster, October and November of 1951, where air blast was measured for the first time from an airburst over land, the observed pressures were considerably lower than predicted. This indicated that there were serious errors in the heights of burst which had been selected for operational use of atomic weapons by the services. The Snapper, or development phase, commenced with shot number 3 and continued through shot number 8. The measured radiochemical yield of this shot was 30.7 kilotons. This yield, being very close to that which had been theoretically predicted, added greatly to the conclusion that this proof test was very successful. This device has taken the form of a small betatron, which was triggered to fire a burst of high-energy gamma rays into the core at the proper time, and thereby produce a neutron flux for initiating the fission reaction. The most difficult feature of this device is triggering the betatron at exactly the right time. The first shot was fired on Frenchman Flat at the same scaled height of burst as Buster Baker in order to see whether a bomb detonated over a smooth, light-colored, and relatively dust-free area produced the same blast pressures as one over the rougher, dustier, and darker areas used for Buster. The blast pressures were measured by gauges flush with the ground and on towers up to 50 feet above the ground. To assist in developing blast theories, the thermal radiation flux and pre-shock air temperature were also measured. The free air pressures were measured by means of smoke trails and puffs. The results of this shot, compared with the following Tumbler shots, indicated that the difference in terrain between Frenchman Flat and the Buster area does not have a major effect on the blast pressure. Shots 2 and 3 were fired back in the Buster area at a higher scaled height of burst than had ever been used before. Comparison of the results of these two shots, one of which had a yield of 1.16 kilotons and the other of 30.7 kilotons, demonstrated the applicability of the normal cube root blast scaling laws. It can be concluded from these shots that the data obtained during Buster was correct, even though it was less than predicted. Shot number 4 was fired at a low height of burst, the same scaled height as used for Buster, Charlie, and Easy, in an attempt to duplicate the peculiar blast pressure situation observed on these shots. On this shot was observed for the first time a precursor pressure wave, which moved out along the ground in advance of the incident and reflected shock waves from the bomb. It will be noted that the precursor wave stirs up a tremendous amount of dust and hot air through which the incident blast wave must travel, and this undoubtedly accounts for the degrading effect observed on the blast pressures. Based primarily on the data from the Tumbler series, it has been possible to develop a set of experimental height of burst curves which should be satisfactory for most operational purposes, recognizing that peculiar target conditions may in some cases alter the pressures obtained. From these curves, it is evident that if one is after strong targets which require an excess of 15 pounds per square inch, then the bomb should be detonated relatively close to the ground. For weak targets requiring 10 pounds per square inch or less, some gain in damage area can be obtained by raising the height of burst. In addition to the basic measurements of blast pressures and thermal radiation, a number of other effects tests were also carried out in connection with the Tumbler snapper operation. Of particular interest was the exposure of aircraft. These included F-47s, B-17s, F-86s, an F-90, a B-29, and a B-45. The bombing aircraft were less resistant to blast pressures than were fighters. Planes oriented head-on were considerably less sensitive than planes tail-on or side-on. Not only did the thermal radiation ignite fabric surfaces at extreme distances, but also contributed to weakening of metal surfaces and increasing their sensitivity to blasts. As a result of the test, sufficient data were collected to establish damage criteria for aircraft on the ground. Test results indicate that revetments do not provide appreciable blast damage protection for aircraft. Another project of considerable interest was the effect of blast and thermal radiation on forests. Data was obtained on forces required to knock over individual trees. Also, data on radiation necessary to ignite forest fuels and to predict possible incidents of forest fires following atomic explosion. As an added dividend to the primary objectives of the Tumbler snapper operation, advantage was taken of the atomic explosions to provide troop indoctrination and orientation. Personnel of the Army, Navy, Air Force, and Marine Corps participated in maneuvers in connection with the shots with the mission of obtaining indoctrination training in tactical employment of atomic devices, training in essential protective measures, information concerning psychological effects on individuals, and indoctrination in the effects of atomic explosions on military equipment, material, and emplacements. This participation resulted in a much more accurate understanding of the potentialities of atomic weapons and aided in the development of some basic tactical doctrines to be applied in using or in defending against the use of tactical atomic weapons. Foxholes and dug-in positions were proven to be the best defense in the field against atomic attack.